chapter 7. It is about the agent's value. So in this chapter, basically, your syllabus will cover two methods. The first method is power method. Okay, power method we can say is actually the in terms of engineering we can call it is a numerical iteration method. We are going to find the dominant, that means the largest agent value, dominant agent value, and its corresponding agent vector. And another method is shifted power method. Shifted power method, where in this shifted power method we are going to find the smallest agent value and its corresponding agent vector. So power method is iteration method that used to find the dominant or the largest agent vector, and then shifted power method is going to find the smallest agent value and corresponding of its agent vector. So basically, for the shifted power method, we have to do 2 times power method, but we have to add another formula so that we can find the smallest agent value. If let's say we have a matrix, a square matrix, let's say we have a square matrix A, where this matrix is n times n, that is a square, either 2 times 2 matrix, 3 times 3, 4 times 4, and so on. And then before this, okay, by the way, before this, when we have we normally resolve the linear equation system. Remember, in our chapter 3, we have, let's say we have a square matrix, and then we have x equal to b. Okay, so this is the square matrix. Okay, this is the matrix, and this actually is the vector. Okay, so before this, when we want to solve these equations, we substitute, right? We substitute A become to is equal to LU, where the L is the lower triangular matrix and U is upper triangular matrix. After we substitute A equal to LU, so we substitute back the A here, become LU x equal to B, and we take the L times Y equal to B, and then we solve Y, and after that we get a Y, substitute U x equal to Y, and then we can find the value of x. So this one is similar from the previous chapter, but in this chapter we are going to solve the agent value and its corresponding agent vector. Okay, because this is actually a vector from the terms ax equal to b become a v equal to a lambda v, where this A is the matrix, the square matrix. Okay, A is the square matrix, and okay, and then lambda is actually the agent's value of matrix A. Okay, so this one is a scalar. It's either can be a constant, it can be a real or complex number. Okay, and then V is, that means the corresponding eigenvector. Okay, V is the eigenvector. Eigenvector. Okay, and this eigenvector is a non-zero value. Have to be a value. So actually, this eigenvector can be many. It depends on the eigenvalue. So one eigenvalue may have a lot of eigenvectors. Okay, back to the just now, the formula just now. So we said A V equal to lambda V. Matrix A times with the eigenvector will be equal to the eigenvalue of the matrix A times with the eigenvector. Okay, so if let's say, okay, this formula, okay, we add in identity matrix, okay, and then I put this matrix as I. Okay, what is the identity matrix? Okay, identity matrix is, let's say for the matrix 2 times 2, that means 1 0 0 1. If for matrix 3 times 3, that means 1 0 0 0 1 0. Okay, this is the identity matrix. Okay, so now when we add in this identity matrix into this equation, so the equation will become AV equal to lambda into, so AV minus lambda I V will equal to 0. Okay, so and then because there is a, here is a V eigenvector and here also have a same eigenvector, so put inside this one 0. So when we get the matrix A minus the eigenvalue times with the identity, okay, and then in the whole this one times with the eigenvector equal to 0, okay, this become one formula. This is a homogeneous linear equations. And then this one, this value, this one, A minus lambda, in the modulus value, let's say this one is equal to 0, this we call this equation, we call as a characteristic equations. When we do the determinants of these characteristic equations, that means like this, determinants of A minus equal to 0, that means this is the characteristic polynomial. Okay, so just now I already tell you that one eigenvalue may have many eigenvector. is really depends. Okay, maybe now we try to do a example. Okay, we do an example. The examples that, okay, it's asked you to show, let's say we show that the agent vector of 2, 1 is an agent vector of matrix A equal to 3, 2, 2. Okay. Corresponding to the agent value of equal to 4. Okay, that means now we want to find whether this matrix A time with the agent vector either is it equal or not with the agent value time with the agent vector. Okay, so this one we don't know whether it is whether this agent vector is the agent vector, this V is agent vector to this agent value or not. Okay, so hey, we have matrix A 3, 2, 3, -2 times with V, is it equal to the agent value time with agent vector, this one V, so we don't know. So this one 3 times 2 plus 2 times 1, and this one is 3 times 2 plus -2 times 1, whether it is same to this one. 4 times 2 8, 4 times 1 4. Okay, so this one 6 plus 2 8, this one 6 minus 2 4. So yes, okay, so that means this agent vector, this is the agent vector of the matrix A corresponding to when the agent value is 4. So just now I already told you that the agent vector can be many. So let's say here we have one agent value here, 4. Right, the agent vector can be, okay, now we already get it, the agent vector is 2, 1. The agent vector can be all those multiply, any non-zero multiple of V will become the agent vector of this corresponding to the agent value of equal to 4. That means either this one V equal to 2, 1, 8, 4, maybe this one, because this one multiplied 2, 4, 2, or maybe 10, 5, and so on. This all will become the agent vectors of corresponding to this agent value of matrix A. Okay, let's try some example. Okay, example. Let's say we have a matrix A equal to 7, 3, 3, -1. Okay, and we have this matrix and try find all the agent value and its corresponding agent vector. So we have matrix A, and then so the step 1, that's mean we want to find, the first thing is the characteristic. Remember just now, characteristic equation. That means A minus lambda times with the identity matrix equal to 0. So that means here we have matrix A 7 3 3 negative 1 minus lambda times with the identity matrix equal to 0, and now become 7 3 3 negative 1 minus lambda 0 0 lambda. Okay. So it's very simple because this is a minus, just 7 minus lambda and 3 minus 0, 3 minus 0, and then negative 1 minus lambda. Okay. So now we begin, this matrix becomes 7 minus lambda 3 3 negative 1 negative lambda minus lambda. So, and then we have to do the determinants of the entries. So we have to do the determinants of the entry. That means determinants of this one. Okay, that means we want to do the determinants of this. Okay, so this entry A minus lambda times with the identity matrix, we already get this one. So that means we want to do the determinants of this matrix. 7 minus lambda 3 3. Right. So okay, the determinants will become 7 minus lambda times with negative 1 minus lambda minus 3 times 3. Then we'll get negative 7 lambda plus lambda square minus 9, and then we will get lambda square minus 6 lambda minus 16. Okay, so if let's say, okay, if let's say these determinants of the entry equal to 0, which means this is the characteristic polynomial. So this is actually characteristic polynomial. So from this one, lambda square minus 6 lambda minus 16 equal to 0. So it's actually lambda minus 8 lambda plus 2 equal to 0. So the eigenvalue is equal to 8 and equal to negative 2. So we will have two eigenvalue here. One is 8 and one is negative 2. So that is 2. One is 8, one is negative. So both this eigenvalue will have its own eigenvector, and this one, this eigenvalue also will have its own eigenvectors. So now we already get the eigenvalues. We have to find the eigenvector of these two eigenvalue. So the next step, we are going to find corresponding eigenvector. So for the eigenvalue is equal to 8, right, we have to find, okay, remember just now we have the equations just now is this one, a minus lambda I, right? We have to time with v equal to 0. Okay, this is actually the formula that we want to solve in order we're going to find the eigenvector, this v. So now this one we already have from the previous one, this one, right? This characteristic equation, a minus lambda I, this one, and if we get 7 minus lambda, 3, 3, 1 minus lambda. So that means here it is a 7 minus lambda, 3, 3, times v equals 0. Okay, so this one now lambda is 8. That means 7 minus 8. Then this 3, 3, 1 minus 1, negative 1 minus 8. And v, because this one is actually is 2 times 1, v1, v2, go to 0. Okay, so 7 minus 8 is negative 1, negative 9, v1, v2. So remember Gauss eliminations. Okay, let's say we have these two linear equations. This means we have negative 1, 3, 3, negative 1. This one we don't know. So this means 0, 0. That means actually this is equal to 0, 0, 0, 0. Okay, so let's say we assume this one as a R1 and this one is R2. So we try to eliminate this one so that we try to make this 3 become 0, right? So that we have to time with negative 3 or negative 1, remember? Okay, and then R1 plus R2. So now it's become this one. Okay, so that means 3 times R1 plus R2. So we will get a new R2. And then we get 3, 0. This one becomes 0. When you put R1 as 3, R2 is negative 9. What do you get? So you get 0 as well. Okay, so I think I hope you probably know how to get this value or this value. So now this is your new R. So this is our R1 and this is a new R2. So from here we know that, okay, negative 1 times with v1 plus 3 v2 equal to 0, because this already 0. So we only have this equation. So 3v2 equal to v1. So let's say let v2 equal to 1. So we get v1 equal to 3. Okay, so and I said just now, so now for the eigenvalue of 8 we will have the eigenvector of 3, 1. This is the one. If let's say we assume this one, because this is formula, so this will be either 3, 1, maybe 6, 2, can be so on, can be like 9, 3, and so on. So that's why one eigenvalue will have many eigenvectors, and this one, this is a one of the corresponding eigenvector. Okay, now the next one, because just now we have two eigenvalue, right? one is 8 and one is -2. So next we are going to find the corresponding of the eigenvector when the eigenvalue is -2. So for the eigenvalue is -2, the same method to 0, 7 minus lambda, 3, 3, -1, -lambda, time with v1, v2 will be equal to 0, 0. And then that means here 7 plus 2, 3, 3, 1 plus 2 equal to 0, 0. That means 9, 3, 3, 1. And this is similar to just now. We have to solve the equation using Gauss elimination, or you can use calculator if you want, so that you'll get, okay, let's say I do this one is R1, this one is R2, and then we try to eliminate this one to become a 0. So that means we have to do 3 minus like R1 so that we can get the new R2. This one is 0, and this one where we put 3, 1, that is also 0 and 0. So that means 9 v1 plus 3 v2 equal to 0. This one is 1, this one is 3. Then 3 v1 equal to negative v2. So let's say we let v2 equal to 1, then we will get v1 is equal to -3. So that means -3, 1. There is the one of the eigenvector of this corresponding to this eigenvalue. So can be -6, 2, and so on. Okay, now we continue with the first method in this eigenvalue chapter. So power method. That I mentioned before, where the power method is actually is the integration method that we are going to find the dominant eigenvalue. This means we have to find the dominant eigenvalue, or we can say that is the largest magnitude. The largest magnitude of the eigenvalue, and its corresponding eigenvector. for the matrix, if let's say for the matrix, square matrix. So we can find the dominant eigenvalue using the power method, where the formula or the power method, okay, normally we have to assume the initial eigenvector value. We have to assume either, if let's say in the questions, in the test or final, either they give you the initial value, or you have to assume your own. That means this value, the formula of the eigenvector k plus 1 will be equal to the matrix A, the square matrix, time with the eigenvector for the level of k over m k plus 1. So this, okay, m k plus 1 is actually the maximum absolute value of matrix A time with the eigenvector at k level. So this one for k equals start from 0, 1, 2, and so on. So this equation you have, okay, we are going to use this equation to do the integration, and this one we call power method. So in the test or final, let's say this power method come out, you no need to memorize, this equation will be given. So just now I said that if let's say question they are asked you to find the dominant eigenvalue, we have to start with the initial eigenvector, where what is the initial eigenvector? That means for the k equal to 0, that means this one v at level 0, k equal to 0. This is the tri-value of eigenvector, or the initial value of eigenvector. Okay, so we will start to do the iterations. Start from, okay, do the iteration, do the power method. Start from v naught, that means the initial eigenvector. We have to do the iteration. We have to do the iteration until, okay, m plus k plus 1 minus mk is less than the epsilon. Okay, so I think this one is similar to the previous chapter, similar to the chapter 3 that we normally use to find the value of x, and until you have to integrate your fx until the last one minus the second last is less than the epsilon. So if let's say that one you are doing the calculation in 3 decimal places, that means you have to be less than 0.005. If you are going to solve your solution using 4 by calculate by 4 decimal places, so that means you have to be this mk minus k plus 1 minus mk in the modulus have to be less than 0.005. Okay, so maybe we try example in your book. So maybe we try in the book. Oh, by the way, sorry, I'm sorry. After you finish, do the integration until you get this value is less than the epsilons. That means the largest, the dominant eigenvalue or say this is lambda 1 is equal to this mk plus 1. and its corresponding eigenvector is v1 is equal to v at the level of k plus 1. So this is what we are going to find, the dominant eigenvalue and its corresponding eigenvector. This one. Okay, now we move to the example in your book. So maybe we try this example 7.3, page 156. So in the question it said that given that the matrix A is this one, use the power method to find the dominant eigenvalue and its corresponding eigenvector for matrix A using the initial eigenvalue is equal to 1, 1, 0 in transpose matrix, and stop the iteration until you get the mk plus 1 minus mk in the modulus and the absolute value is less or equal to 0.0005. Okay, so back to the questions. We are given A, matrix A is equal to 4, 3, 0, 3, 4, negative 1, 0, negative 1, 4. Okay, and we are given as the initial value of the eigenvector is 1, 1, 0. Okay, this means transpose matrix. This means it's actually 1, 1. Okay, this one. So the first thing, okay, we already have this one. The tri value of v naught. Okay, so the next step, we have to perform matrix multiplications. That means matrix A times with matrix V. So back to the formula. Remember the formula is 1 A times V for the K level. So for K, start from 0, 1, and so on. So for K equal to 0, A, B, 0 equal to matrix A time with the tri value of V naught, this one, 1, 1, 0. So just multiply it, what we will get. So that means we will get 4 times 1 plus 3 times 1 plus 0. 3 times 1 plus 4 times 1 plus negative 1 times 0. And then 0 plus negative 1 times 1 plus 4 times 0. So we will get 4 plus 3, 7. 3 plus 4, 7. And minus 1. Right. So this is the value of the multiplication of the matrix A with V, and then we have to find the so the next step, we have to find the dominant value, that means in absolute value, modulus, for the components of A and B. Okay, we have to find the dominant value for the component A times V from what we get from here, 771. Here, that means the dominant value is 7. Either this one or this one. That means the dominant value is 7. So, and then that means our first dominant value is equal to 7. Or that means we can say this one is our k plus 1. So here from this one we have to change to, we take the nominal value, put outside, and then that means 7 here, that means 1 here, and negative 1 over 7. Okay, so this will be the value. This is the value of A, mk plus 1, and this is the value of the next V. Now this one is V0, so this is V1. You know what I mean? So if we go back to the formula just now, remember I said that the V k plus 1 is equal to AV k over mk plus 1. Okay, let's say now we want to find V, the eigenvector for first level. That means we have to do this 0 over 7. Okay, so from here, because this one is the dominant value, so this here, that means we take out the dominant value. So now you try to solve, okay, whether this one is same to this one or not. So let's say this one, we get the value, this one, right? This one 7 over 7, that means 1. And then this one 7 over 7, 1. And this one negative 1 over 7, that means negative 1 over 7. So this is the most simple. If let's say if this all calculation we can do in the table, because we have to do the integration until we only can stop, go back to the questions, when the mk plus 1 minus mk is less than 0.0005. So the simplest way we do in the table. So in this table, we will write, okay, we will have k, okay, and then we have the eigenvector, and then we have eigenvector, because this one in the transpose form, and then we have matrix A times V, and also in the transpose form, and then this one mk plus 1. So go back to just now, we already solved this one. For the k level, k is for the level k equal to 0, that means for the k level equal to 0, we have the first initial try value of V0, this initial value of eigenvector, that means 1 1, that means 1 1 0 1 1 0 1 1 0. Okay, and then we solve. Okay, this one just put in calculation in the calculator, that means we have matrix. Okay, if you are using the old calculator, this one, okay, so make sure you have to choose in matrix mode, mat. Okay, now you have to key in this matrix, so shift 4 dim. Okay, now key in matrix A. So matrix A is 3 times 3 matrix, 3 times 3. So A11 is this value, 4 equal to 3 equal to 0, 3, 4, negative 1, 0, negative 1, 4. Okay, so after you key in all the equation, now key in another matrix. That means this matrix, this vector, the tri-value of V0. So I assume I put this one as a matrix B too. So matrix B is 3 times 1, 3 times 1, because this has a 3 rows and 1 column. So this matrix is 3 times 1 matrix. So the value for this one, matrix B, 1 1 is 1, 2 1 is 1, 3 1 is 0. Okay, now we already have matrix A and matrix B. So now we have to multiply matrix A with the matrix B. So that means shift 4 matrix A time shift 4, sorry, okay, I go back again, shift 4, okay, matrix, choose matrix A, okay, time shift 4 again, matrix B, matrix A times matrix B. So equal, okay, you will get equal to 7 down, 7 and then negative 1, right? So this is same as just now we calculate manual. Okay, so from this one, this 3 value here, 7, 7, negative 1, the dominant value in absolute is 7. So we choose M, K plus 1 is 7. So for the next iteration, for the K level, K equal to 1, the value of this V is actually this value divided by this value. That means 7 divide by 7. That means 1. 7 divided by 7, 1. Negative 1 divided by 7. That means negative 1 over 7 or negative 1 7. So we get negative 0.1429. Okay, so now matrix A still same. Now your matrix B already changed from 110 to 11 negative 0.1429. So now you have to key in your matrix B again. Shift 4 dim matrix B, 3 times 1, still 3 times 1. So matrix B is 1. Yes, 1. This one is negative 0.1429. Okay, and then we have to multiply matrix A with matrix B. So shift matrix A times matrix B. So we'll get the value 7.1429 negative 1.5716. Okay, from these 3 value, the dominant value, the largest value in a modulus is this value, right? 7.1429. Okay, so that's the next level. K equal to 2 becomes 7 divided by this one. So that means 7 divided by 7.1429. So you get this value is 0.99800. Okay, and this one is 1. This one negative 1.5716 divided by 7.1429. We get negative 0.2200. Okay, so now change the matrix B again. Matrix B, 0.81, negative 0.22. Okay, matrix A times matrix B. So we get 6.92, 7.16, negative 1.88. Okay, this one, okay, modulus, choose the dominant. If let's say this one is negative 10, so you have to take negative 10. Okay, we don't mind the positive negative signs. Okay, now the dominant is 7.16. Okay, so the next iteration is this one, 6.92 divided by 7.16. That's 6. So we get 0.9665, right? And this is 1. This is negative 1.88 divided by 7. Negative 0.2626. Okay, and then now key in a new matrix B again. 0.51, negative 0.2626. Okay, and then matrix A times matrix B. 7.1621, negative 2.004. So from these three values, the dominant value is this one, 7.1621. So we still cannot stop, because now this one minus this one, okay, still 0.00 to 1. Okay, so we still have to do the iteration, the next iteration. So this one, for the next one, 6.866 divided by this dominant value, 7.1621, we get 0.95, 0.9587. This one, the fourth iteration for the fourth times, and then this one is 1, negative 2.0504 divided by 7.162. Negative 2. Okay, so key in again matrix B, the new value of matrix B, then the nominal value is 7.1624. 1624 minus 7.1624 minus 7.1621 is 0.003, is it? Okay. So this means we can stop, but then we have to, because this one is the level k plus 1, so we have to do another one. This one is level k plus 1, this one is level 4. That means this value is belong to the this Eigen vector. Okay, so this we can stop at this. Is there something wrong with this value? 2626. Go back, because mine is a bit different with the books. We try to do this one back. Okay, matrix A times matrix B. Because I get the difference from the example in the books. Okay, so now the next iteration is, okay, this Eigen vector is 7.16 6.8348 divided 0 3 1 okay. So sin m, this one is m k plus 1, this means n5 minus n4 is equal to 0.0003, that means less than 0.0005. So the dominant eigenvalue, let's mean on that, is equal to m5, this one, m5 7.1624, and it corresponding eigenvector is v1 is equal to v5, sorry, should be v5, equal to 9543 transpose. So this all. Okay, so I think that's you may try some other example in the books or maybe exercise. So this is the end of these sections. So maybe we'll continue shifted power method for the next section. So thank you very much.